So the last information we're going to learn is about acids and bases. There are 3 definitions of acids and bases that you need to know. The first definition is the Arrhenius definition of an acid or a base. All right, this is what you probably think of when you're told, oh, this substance is an acid or this substance is a base. Acids, based on the Arrhenius definition, are substances that produce hydrogen ions, H+ ions, in solution. And bases are substances that produce hydroxide ions, OH- ions, in solution. Okay, very straightforward. The second definition for acids and bases is Bronsted-Lowry. Bronsted-Lowry. A Bronsted-Lowry acid is pretty much the same as an Arrhenius acid, where it donates an H+. A base, though, is different. Instead of donating OH-, it's accepting H+. So let me talk a little bit about why we can call H+ a proton and why we can use that word instead of H+. So let's think about the hydrogen atom. How many protons does the hydrogen atom have? 1 proton. How many electrons does the neutral hydrogen atom have? 1. And on average, the majority of the isotopes of hydrogen have 0 neutrons. So most of the hydrogen atoms are just a proton surrounded by an electron. And if we ionize that and make it H+, what did we do? We took away the electron. And therefore, what's left over? Just a proton, which is why we can call H+ ions protons. So whenever you hear something about like protons in terms of like solution and stuff like that, it's talking about H+ ions. If you've ever taken, have you ever heard of the medicine Nexium? It's for acid reflux. Okay, acid reflux is like chronic heartburn. So Nexium is a class of drugs called proton pump inhibitors. The way Nexium works, let me back up. People with acid reflux, they often get it because of an excess acid. Their body produces too much stomach acid that then causes heartburn. So Nexium, it's a PPI, proton pump inhibitor. What it does is it reduces the amount of acid that is produced. It's a proton H+ pump inhibitor. It's inhibiting how much H+ is being pumped into the stomach. So, yeah, fun fact. Okay. And the third definition of acids and bases is Lewis acid and base. We're not going to deal with this too much. Just know the definitions. A Lewis acid is a lone pair acceptor, and a Lewis base is a lone pair donor. All right. Strong acids and strong bases. There are 6 strong acids that you need to know. There are more than 6, but I'm only requiring you to know 6. All right? And they are HCl, HBr, HI, HNO3, H2SO4, and HClO4. And I'll write the names below. Okay. HCl. Anyone remember what the name of HCl is? Hydrochloric acid. I'm not going to include the word acid because of the space issue. But that's hydrochloric. What's HBr? Hydrobromic. What about HI? Hydroiodic. HNO3?
Nitric acid.
Nitric. H2SO4? Sulfuric. Hold on. And this last one, HClO4, ClO4 minus is not a polyatomic ion that I asked you to memorize, but that's ClO4 minus is perchlorate, so this would be perchloric. And all of these are acids, okay? So I suggest making note of these strong acids somewhere so that you don't forget them, index that information away. All right, strong bases. The strong bases are group 1 metals with hydroxide, and then strontium and barium with hydroxide. So like a group 1 metal like sodium. Sodium hydroxide is a strong base. Lithium hydroxide is a strong base. Strontium hydroxide is a strong base. But like aluminum hydroxide is a weak base. Or like, I don't know, silver hydroxide would be a weak base. Okay. All right, now we're going to write a couple reactions, talking about neutralization reactions and Bronsted-Lowry acid-base reactions, and then we'll jump into the pH scale and doing calculations. Okay. So a neutralization reaction is a type of double replacement reaction. And these neutralization reactions are going to be based off of the Arrhenius definitions of acids and bases. Okay? In a neutralization reaction, we have an acid reacting with a base, producing water and a salt. Now, when I say a salt, I don't mean solely sodium chloride. Sodium chloride is a salt, but it is not the only salt. A salt is just an ionic compound that is not an acid or a base. That's really just, a salt is like a classification of a compound. Okay? So, for example, here we have sodium hydroxide reacts with hydrochloric acid. How do I write sodium hydroxide? NaOH. And what is it reacting with? HCl. What type of substance is NaOH? Is it my acid or my base? Base. It is my base. Guys, can you knock it off? What type of substance is HCl? My acid. Now this is a double replacement reaction, so the H plus and the OH are going to switch places. And what is this going to form? Yeah, it produces water and a salt. So H2O and, in this case, NaCl. All right. H2O is obviously my water. And NaCl is my salt. What do we need to do with this reaction? Balance it. So what are the coefficients when this is balanced? 1, 1, 1, 1. It's already balanced. Isn't that nice? Okay. We're going to do another example of a neutralization reaction, and then we'll get into the other type of reaction. Phosphoric acid reacts with calcium hydroxide. So phosphoric acid is written like this, H3PO4. I'm not going to worry about the tape matter. Notice how that was not on our list of strong acids. This is a weak acid, okay, because it's not strong, it's weak. So only two options. So this is my acid. And then it's reacting with calcium hydroxide, which is CaOH2, which is also not on the list of strong bases, so this is a weak base. But this is my base. What's one of the products of neutralization reactions? H2O. always going to be producing water. So this is producing water. And what's left over? The calcium and the phosphate. The calcium and the phosphate. Ca3PO4 2. So this is my water, and this is my salt. I definitely suggest you go back and review the ionic charges and how to write ionic compounds prior to this test. Okay? Maybe make note of those polyatomic ions. All right, what do we need to do with this reaction? Balance it. So when this reaction is balanced, when you're balancing this, it might be helpful to write water as HOH instead of H2O, where the first H in HOH comes from the H in the acid, and the second, or the OH comes from the OH in the base. It might be helpful to break it down like that because it makes balancing a little bit easier, okay? Has anyone balanced it yet? What do we get? 3261? I did not get 3261. I got 2361. Is that what you said? I just heard you wrong? Okay. 2361. So go back and review balancing. Okay. This unit's kind of like the culminating unit. Everything's coming together. I'm assuming we're going to the next page. All right. Come on, next page. There we go. Weak acids and weak bases. These Bronsted-Lowry reactions, okay? These Bronsted-Lowry reactions. So, we'll talk about the conjugate acid and conjugate base in just a moment. Let's write out this reaction. We have acetic acid reacting with water. Acetic acid is HC2H3O2, and it's reacting with water. Water, or let me back up. What type of substance is acetic acid? It's an acid, right? Water is a special type of substance. Water is amphoteric, which means it can act as either an acid or a base. Okay, depending upon what it's reacting with. So since water is reacting with an acid, water is taking on the role of being a base. Okay, in this reaction. If water were reacting with a base, then it would take on the role of an acid. So it's really special. It can kind of do whatever is needed. All right. Now this is a Bronsted-Lowry reaction. In this reaction, what's going to end up happening is Bronsted-Lowry acids donate H+ ions or protons, and the bases accept protons. So the hydrogen in my acid, this hydrogen here is going to be transferred to the water. Okay? And the products will be the ions that those form. What did I just draw? It's that equilibrium arrow that we did on Monday, right? Monday? Wednesday. No, Monday. Wednesday was the lab. Monday. The equilibrium arrow that we just learned the last class we did notes. Remember, that means that the reaction can occur in either direction. Okay? So my products are going to be C2H3O2 minus and H3O plus. And now my acetate ion, the C2H3O2 minus, that is called my conjugate base because it is the substance that is left over after the acid got rid of that proton. Okay? And then H3O plus is my conjugate acid, which is the substance that remains after that base accepted a hydrogen ion. The products of Bronsted-Lowry reactions are always ions. Okay? That is the nice thing about them. Or at least at this level, they're always going to be ions. Also, what do you notice about the balancing for this reaction? What? It's already balanced. Bronsted-Lowry reactions, for the most part, or at least for everything you're going to see, always going to be balanced already. Even at the AP level, we only deal with the ones that are already balanced. Okay. We spend an entire 2 units doing this type of stuff in AP chemistry, so have fun with that. Now for the pH scale. Now for the pH scale. The one that's in your handout, I do apologize that the quality isn't the greatest. I've put this better one, which I really just took the one that was in your handout and I retyped it. This is already on Vision, so you can reference it so you can see the nicer one and you can make note of any pertinent information from the better looking pH chart. But the pH scale, like you've seen it before, right? You've seen a pH scale at least one time in your life prior to this class. So a pH scale is a negative log-based scale, meaning when the pH is low, it means there's a lot of hydrogen ions in solution. And then when the pH is high, that means it's really basic, there's not a lot of hydrogen ions. Okay? So up here, at the top of this chart is where the substances are more acidic. That means we have a low pH or high hydrogen ion concentration. Remember, those brackets mean concentration. We learned that on Monday. And then down here, at the bottom of the chart, this is where the substances are more basic. We have a high pH or a low hydrogen ion concentration. All right, and I've provided, there are some examples in there as to how acidic or basic those substances are. All right, so we're going to do some calculations with, or we're going to do some calculations of pH.
Is rainwater?
Yes, rainwater is slightly acidic.
Okay, so it's not that acidic, right?
No, but it's slightly acidic. When you drink coffee, you drink Coca-Cola, that's even more acidic. You eat tomatoes. All right. So you have this square thing. This is a very useful tool. This is a very useful tool. Very useful tool. It does look index card shaped, doesn't it? All right. I'm going to come back to this page. Let's look at this. What we're going to do is from this is what our homework is. We're going to calculate those 4 things. We're going to find pH, we're going to find H plus concentration, OH minus concentration, pH, and POH. Okay, using all the formulas written on this chart. Okay? So first of all, HBr. We have a 0.15 molar solution of HBr. What type of substance is HBr?
Acid.
It's an acid. We know it's an acid because, and because it begins with H. But this is an acid, right? The concentration of H plus will equal the concentration of our acid. Because HBr has H plus in it. So that's going to equal the concentration of my H plus. So therefore, my H plus concentration for this problem is 0.15 molar. Now we're going to do calculations to find the other three. So looking here, we have H plus. We want to find the other three. The first one we want to find, though, is OH minus. To get from H plus to OH minus, we're going to use this formula. Okay? Kw equals H plus times OH minus. Kw is a constant, and it is always 1.0 times 10 to the negative 14. That's not going to change. Okay? So, let me change colors. Kw equals H plus times OH minus. We're finding OH minus, so if I rearrange this formula, I'm going to have Kw over H plus. And that will equal the OH minus concentration. So I can plug in what I have. 1.0 times 10 to the negative 14. That is a value that's never going to change. We're going to divide that by the concentration of my H plus, which is 0.15. And that will get me my OH minus concentration. So go ahead and do that calculation on your calculators. So what do you get? What do you get?
I got 6.6.
266.
6.7 e to the negative 4.
That's what I got. 6.7 times 10 to the negative 14 molar. If you didn't get that, we can talk through towards the end of class about making sure you're plugging in your calculator correctly. But you understand, it's just rearranging the formula. Really, it's just plug and chug of the formula. Okay. Now, we have the bottom two. We want to find the top two. So how are we going to find pH? Well, let's follow the line. We're going to go from H plus to pH. We're going to use the negative log of H plus concentration. pH equals negative log of H plus. So we're going to type negative log of 0.15, and that will equal my pH. So when you type that in your calculator, negative log, 0.15, enter, what do you get? 0.82. And the nice thing is there are no units for pH or pOH. No units. And now to find pOH, that's the only one we're missing. To find pOH, how can we get there? We could do pOH equals negative log of OH minus. We could use this. Is there another way? pH plus pOH always equals 14. Okay, so once you have three of them, it's really easy to find the fourth one. You have multiple ways. I'm going to do the top equation, though. The pH plus pOH equals 14. Okay, So then to solve that, we're going to take 14 minus the pH to get me the pOH. So what is 14 minus 0.82? What is 14 minus 0.82? 13.18. And again, no units on pOH. In the next problem, we're going to talk about the sig figs of pHs and pOHs. Are we ready? Okay. What type of substance is NaOH? It's a base because it ends in hydroxide. We have OH minus ions. So which concentration can I get from the base concentration? The OH concentration. So the OH minus concentration is going to equal the concentration of my base, in this case NaOH. So what is my hydroxide ion concentration? .0500 molar. And now that I have one, I can find the other three very easily using that chart. So to find H+, we're going to use that KW formula. But this time I know OH already, so I'm going to take KW over OH to get me H. So 1.0 times 10 to the negative 14 over 0.0500 molar. How many sig figs this time? How many sig figs does that hydroxide ion concentration have? 3. That the leading zeros don't count, but the lagging zeros do. So what is 1.0 times 10 to the negative 14 divided by 0.0500? Yep, 2.00 times 10 to the negative 13 molar, and that's my H+ concentration. All right, now we just have to find the other two, right? How can we find pH and pOH? Just negative log of the H+ and the OH minus. So for pH, I'm going to take negative log of my H+, negative log of what I just solved. Now here's where I want to talk about sig figs. So if you're writing in pen, don't write down anything yet, okay? Other than what I've written so far. Like you can write down the work, but don't write down the answer. When you do the calculation, like how many sig figs does that, back up. How many significant figures does my H+ concentration have? 3. Has 3 significant figures. So my pH needs to have 3 significant figures. But the way you do sig figs with pH is a little bit weird. This answer with proper sig figs, and you can write this down, is 12.699. The reason why the sig figs are weird here is because it's a log-based scale. The 12 just tells you kind of the order of magnitude for the power of 10 that you're using. So the rule for sig figs. The rules for sig figs for pH and pOH is The number of digits after the decimal is the number of significant figures. So since my 2.00 times 10 to the negative 13 had 3 sig figs, I needed to have 3 numbers after the decimal point. The numbers that come before the decimal point are there, but they don't count for significant figures. Okay? So actually, let me not say the number of digits. The digits after the decimal are the significant figures. Okay? So only the digits that are after the decimal are the significant digits in the PH or POH. Let me pause. All right, so now to find POH, let's do the negative log of OH minus. This way we can practice doing the sig figs. So negative log, my OH minus is 0.0500. How many sig figs is that? 3, because that's normal sig fig rules. It's when we convert it to the POH that we have to worry about only having 3 decimals or 3 digits after the decimal. Okay? So what is negative log of 0.05? 1.301, right? Not 1.30, not just 1.3, but 1.301. I know that looks like 4 sig figs, but it's only 3 because we only count what's after the decimal point. And that's my POH. And you can verify if you add the pH and the POH together, we're going to get 14. So that's another way to know that you did the problem correctly. That's what your homework is. Your homework is a big chart where you're given one of the 4 components and you have to find the other 3. And then say if it's acidic or basic. Okay. We have one more topic within today's notes, and that is titrations, and then we'll be done. Are you ready? All right. Titrations. Titrations. A titration is an experimental process that is used to determine the concentration of a substance, most often an acid or a base. Okay? So in a titration, the piece of equipment that we use is called a burette. Okay? We haven't used a burette in a while. We looked at them at the beginning of the year, but it's a burette. A burette is used to deliver a specific amount, and you can measure how much of the substance you've delivered. What you're adding is called the titrant. This is the substance that has a known concentration. So that's a substance we know the concentration of, and it's being added to the substance we don't know the concentration of, which is called the analyte. Oftentimes, an indicator is used to determine the exact point at which the reaction has occurred, like when they've been completely neutralized. An indicator is a solution that will change color depending upon the pH that it's in. The most common indicator that we use is phenolphthalein. I know that word looks crazy, and there's 5 consonants in a row, but that is spelled correctly. Phenolphthalein. Phenolphthalein is fuchsia in basic solutions, which is kind of the color that I'm using, and it's colorless or clear in acidic solutions. So when it's neutral, it's going to be like a light pink, kind of like the color of this sheet right here. Okay, it's like a light pink. Another way, I'm not going to read through this, but another thing is litmus paper. You can read. Or like pH paper. You can also use a pH probe to actually measure the actual pH throughout it, not just estimating with other stuff, okay? Are we good here? The end point of the titration, where that indicator, where phenolphthalein would be a light pink, the end point, the neutralization point, is when the moles of the acid are equal to the moles of the base. By knowing this relationship, we can use this formula, MAVA equals MBVB, to find the concentration that we're looking for. This formula should look really familiar to you. It looks like the dilution formula, right? M1V1 equals M2V2. It is the same formula, but instead of 1s and 2s, we're using A's and B's. What do you think the A stands for? Acid. And the B stands for? Base. Yay. All right. So for example, if 25 milliliters of 1.5 molar solution of NaOH is used to neutralize 35 milliliters of HCl, what is the concentration of the HCl? So we're using this formula, MAVA equals MBVB. So let's identify what we have and what we're trying to find. What type of solution is NaOH? That's a base. So that means I know the concentration, the molarity, and the volume of the base. What concentration of base do I have? 1.5. And what volume of base did I use? $25 milliliters. In the problem. Which of these am I trying to find, MA or VA? MA, because that's the concentration of the HCl solution that I've been asked to solve. And I used 35 milliliters of my acid. So we're solving for MA. MA equals MB VB over VA. And we're just going to plug in the values and solve. So what do you get as the concentration of the acid? 1.1 molar? And that was HCl. And now we're done.